Let us now discuss problem number 8. A beam with a span of 7.2 meter between support has an overhang of 2.4 meter on one side only. The beam carries a uniform dead load of 12 kN per meter, including its own weight, and a uniform live load of 10 kN per meter. Design the beam for flexure alone. So hahanapin natin yung dimensions, or we're going to design the dimensions and reinforcement of our given beam given yung mga loadings natin. So with this, hanapin muna natin yung value ng ultimate uniform load natin. And we're going to use NSCP 2015 here. So gamitin na lang natin is NSCP 2015. So with that, sa pagkuha ng loads natin, using NSCP 2015, that is ultimate is equals to 1.2 dead load plus 1.6 live load. So with this one, para makuha natin yung uniformly distributed load natin na ultimate, so we have 1.2, yung given na uniformly distributed load in dead load, that is 12 kN, plus 1.6 sa live load naman, yung given, that is equal to 10 kN per meter. So you have a total uniformly distributed load na 30.4 kN meter. So ito na ngayon yung factored load natin. So with that, kung mayroon tayong WU na 30.4 kN per meter, we will now solve yung mga reactions natin at A and yung reaction natin sa B. So paano po natin gagawin yon? So let's say we will take summation moment at A is equals to 0. So with that, yung rotation natin that is equal to, bigyan natin is counterclockwise is positive. So you have yung reaction natin at B that is counterclockwise. Meron tayong moment arm na 7.2 minus. So next naman, siyempre, yung uniformly distributed load natin. So kung moment natin siya sa A, that is in clockwise rotation. So meron tayong 30.4. And then, imumultiply natin yan to the length na 7.2 plus 2.4. So you will have 9.6 multiplied by the moment arm of 9.6 over 2 is equals to 0. So you will have a value of your reaction at B, which is equal to 194.56 kilonewton. And we're going to have summation forces, vertical is equal to 0, upward positive. So you have a reaction at A plus yung reaction natin sa B na 194.56 minus etong downward load natin na 30.4 multiplied by 9.6 is equal to 0. So yung reaction at A natin, so that will be equal to 97.28 kilonewton. So meron tayo dito na upward force na RA that is equal to 97.28 kilonewton. And yung reaction at B natin, that is equal to 194.56 kilonewton. So with this one, so kailangan nating malaman yung maximum moment natin dyan. So you may do so yung cutting off section natin, or you can do yung shear and moment diagram natin. So mag-shear and moment diagram na lang tayo to compute yung mga values natin. So let us now calculate yung mga moments natin. So siyempre, kung titingnan natin dito, no, meron tayo dito. So solve muna natin yung shear diagram natin. So tataas daw tayo ng 97.28 kilonewton dito. And then, since meron tayong value, 97.28 minus yung 30.4 multiplied by 7.2. So that will become equal to So meron tayong value dyan which is equal to negative 121.60 kilonewton. And then, at point B, tataas tayo ng 194.56. So negative 121.16 plus 194.56. So you will have a value of positive 72.96 kilonewton. So tataas ngayon tayo dyan. And next is 71.96 minus 30.4 multiplied by 2.4. So you will have a value of 0. So this will now become your shear diagram. Next naman is hanapin naman natin yung moment diagram natin. So with this, ito yung moment diagram natin. So meron tayong shear diagram. This will be your moment diagram. So since meron tayong 0 shear, include natin siya sa procedure. So in computing for your 0 shear, so i-include natin yan dun sa moment diagram natin. So we will have an additional point. So let's say yung additional point natin, ano ba? Sabihin natin na that is the point D. Ito yung point D natin. So hanapin muna natin yung value ng location ng 0 shear natin. So with this, we can now use yung similar triangles natin. So by similar triangles, so you will have, so sabihin natin this is X. And siyempre yung matitira, that is equal to 7.2 minus X. So by similar triangles, so eto yan, so base X over yung height ng isang triangle na 97.28 is equals to base, so which is equal to 7.2 minus X over yung height ng triangle natin, despite kung negative yan, kasi kukunin lang naman natin is distance, kaya na-neglect natin yung negative sign. So you have 120.16. By chip solve, the value of your X is equals to 3.2 meter. So with that, meron na tayong given ng mga distances natin. Makukuha na natin yung value ng mga maximum moment natin. So, if we were going to have, di ba, para makuha natin yung moment natin dito, since nagbaba yung value from 97.28 naging 0, so you will have concave, downward tayo, or malulungkot yung beam natin. So 1/2 of 3.2 multiplied by 97.28, so you will have a value of positive 155.648 kilonewton meter. Ayan. So next naman, ito yung moment natin na 155.648 minus, meron tayo ditong negative area. So, minus 1/2 of 7.2 minus 3.2 multiplied by 121.16. So, we will have a value of negative 87.552. So, this will become negative 87.552 kilonewton meter. And lastly, meron tayong negative 87.552. Tapos meron tayong positive area plus 1/2 of 72.96 multiplied by 2.4. So yung value natin dyan is equal to 0. So kung mapapansin natin, ito yung diagram natin. Okay? So with this one, so meron tayo dito na positive moment. Tapos meron tayo dito negative moment. So with this values ng mga moments natin, we will going to design yung beam natin. So first of all, kunin muna natin yung value ng rho natin and establish yung dimension ng beam natin. Sir, paano po natin i-establish yan? So we're going to assume for the value of your rho. So for the step B, so paano natin kukunin yan? So yung rho natin, that will become 0.6 of rho max. Rho max natin in rho max natin in transition control. So with this one, so what is the value of your rho max? In rho max TC natin, that is 0.85 F prime C multiplied by beta over Fy multiplied by 3 over 8. So with this one, yung beta natin, since gagamitin natin is NSCP 2015, so mangyayari niyan dito is 35, yung limiting value niya is hanggang 28 lang. Tapos, yung na-exceed niya, yung value na 35 megapascal. So, gagamit tayo ng formula sa pagkuha ng beta natin. So, beta is now equal to 0.85 minus 0.05 over 7 multiplied by yung 35 minus 28. So, you will have a value of your beta which is equal to 0.18. So, yung 0.18 natin, that is greater than 0.65. So, gagamitin natin is 0.18. So, kapag naman nalagpasan naman, yung mga values natin hasagada, that is 0.65. So, we can now calculate for your rho max. So, yung value ng rho max natin, that will become 0.0215. Kaso nga lang, gagamitin natin rho that is 60% of 0.0215. So, the value of your rho is now equal to 0.0129. So, with this, we will now use yung formula natin for mu max para makuha natin yung mga dimensions natin. So, you have reduction factor multiplied by the nominal resistance, BD squared. So, rho, yung formula natin for nominal resistance, that is rho Fy, multiplied by 1 minus rho Fy over 1.7 of F prime C, multiplied by BD squared. So, with this one, meron tayong given na rho, na mu max dito sa positive, which is equal to, so meron tayong positive mu max natin, which is equal to 155.648 kilonewton meter, negative na mu max natin, which is equal to 87.552. So with this, meron tayong mu max na 155.648. So times 10 raised to 6 para maging Newton mm is equals to 0.90. So yung rho na gagamitin natin, that is 0.0129. Yung Fy natin, that is 415. And yung hinahanap natin na BD squared, 1 minus 0.0129. Yung Fy natin, that is 415 over 1.7. Yung F prime C natin, that is 35 megapascal. So you will have a BD squared which is equal to the value of 35.498 times 10 raised to 6. Next, after that, we will just try. Sabihin natin, try. B is equal to 250 mm. So, yung value ng D natin, that will become the square root of 35.498 times 10 raised to 6 over 250. So, you will have a value of your effective depth, which is equal to 376.82. Kaso nga lang, sabi ko nga sa inyo, dapat divisible by 50s tayo. That's why we're going to approximate that to 400 mm. So if you have a 400 mm effective depth, so para makuha natin yung total depth natin, so we will add a structural covering or sa concrete cover natin na 50 mm. So you will have a total height of your beam which is equal to 450 mm. So, ito na ngayon yung i-consider natin na dimension ng beam natin. So, we're going to try 250 by 450 mm. And for the next step naman, we're going to provide reinforcement naman to our positive and negative moment. So dito dinesign na natin yung cross-section ng beam natin based dun sa maximum moment natin na 155.648. Ngayon naman, we're going to compute for steel reinforcement in tension sa positive and negative moment. So unahin muna natin yung MU max positive natin, or eto yan, which is equal to reduction factor rho Fy BD squared 1 minus rho Fy over 1.7 F prime C. So with this one, meron tayo dito na 155. So 155.648 times 10 raised to 6 Newton mm. Reduction factor is 0.90. Yung rho natin, ito yung hahanapin natin value, yung rho. And then yung Fy natin na 415. Yung D natin that is equal to 250. Yung effective depth that is 400 squared multiplied by 1 minus yung rho na hahanapin, 415, over 1.7. Yung F prime C natin na 35 megapascal. So you will have a value of your rho na gagamitin natin, which is equal to 0.0113. And rho that is equal to AS over BD. So we can now calculate for the value of your AS, which is equal to rho, the 0.0113, multiplied by B na 250, multiplied by the effective depth of 400. So you will have the area of your steel reinforcement, which is equal to 1,130 mm squared. And with that, mahahanap na ngayon natin yung number of steel bars na gagamitin natin dito. So again, kinuha lang natin using shear and moment diagram yung positive MU max natin at saka negative MU max natin. So with this, meron tayong 155.648 at saka sa MU max naman natin na highest, that is negative 87.552 kilonewton meter. So sa pagdidesign natin, we're going to use 25 mm main bars. So with this given AS natin na 1,130 mm squared. So yung area ng isang bakal natin, that is 25 mm squared. So yung number of pieces natin, that will be equal to 2.3 pieces. Or round up natin, kasi nga, wala naman tayong butal na bakal. So we have 3 pieces at bottom reinforcement. Sir, bakit po bottom reinforcement yan? So if you're going to draw the elastic curve of this one, so mangyayari niyan is meron tayong given dito, di ba? So mangyayari niyan, this beam will deflect like this one. So kapag meron tayong, di ba, yung positive moment natin, so draw natin ulit. Ayan. So eto yan. Okay. So kung to-draw natin yung moment natin ulit, so nandito yung, eto yung A, eto yung B natin, eto yung C. Tama? So if you're going to draw that one, pag ganito yan, so positive moment, and then pag yung negative moment tayo dito, and then magsasara doon. So for this one, yung tendency niyan dito is meron tayo dito na positive. So nandito yung positive 155.648. And then dun sa kabila naman is you have a value of negative 87.552. So ito yung point of inflection natin. So at point of inflection, doon mag-change yung elastic curve natin. So with this one, so let's say nandito yung point of inflection natin. So meaning to say, at this point, yung mangyayari niyan, since meron tayong positive moment, so kapag positive moment yung ginagawa, yung response ng beam natin, kapag magde-deflect is ngingiti yan. Kapag naman negative moment, yung response ng beam natin sa pag-deflect is magsa-sad face yan or concave downward. So meaning to say, at this point, since dito is yung pag-deflect niya is pag ganyan yan. Ayan. And then, at the point of inflection, magbabago ngayon. From concave upward, magko-concave downward yan. Dadaan siya dito. Ayan. So, ganito na ngayon yung deflection niya. So, magsi-zero yung deflection sa mga supports natin. Kaya from concave downward, biglang nag-shift to concave upward. So, ganito ngayon magde-deflect yung beam natin. So, meaning to say, at this point, ito yung location ng maximum moment natin. So, nandito yung positive MU max natin. So, dito ngayon, since yung compression natin sa taas, tension sa baba, kaya yung tension natin nasa bottom part, kaya at bottom reinforcement tayo. So, yun yung reason kung bakit bottom reinforcement yung na-design natin. So, next naman, we're going to design naman yung negative MU max natin. So, what is that one? So, etong negative MU max natin, which is equal to 87.552 kilonewton meter. So, kapag negative naman, yung tendency is, mangyayari is, magsasad phase yung beam natin. So, kung nagsad phase yung beam natin, so dito naman, kung kanina is from compression tension, dito naman is, nasa taas yung tension natin, nasa baba naman yung compression. So, with this one, gagamitin lang natin yung formula natin for MU, capacity natin. So, that is rho Fy multiplied by 1 minus rho Fy over 1.7 of F prime C. And then, multiplied by BD squared. So, kunin natin yung mga values natin. Yung MU natin dito, for negative for negative yung consider natin, 87.552 times 10 raised to 6 para maging Newton mm is equals to 0.90 yung value ng rho natin. Hanapin natin yung value ng rho 415 for the value of your Fy BD squared. So given pala yung BD natin, ito yung nakuha natin kanina. Yung kinonsider natin yung maximum moment natin na 155.648. So you have a B which is equal to 250. Yung effective depth natin, that is equal to 400 squared multiplied by 1 minus rho 415 multiplied by 1.7 of your F prime C na 35 megapascal. So by shift solve, we can now calculate for the value of your rho, which is equal to 0.0061. And para makuha natin yung total reinforcement, yung rho natin, i-multiply natin siya sa BD. So yung B natin, that is 250 mm. Yung D natin, that is 400 mm. So you will have a total reinforcement of 610 mm squared. So para makuha natin yung number of pieces, so 610 mm squared, divide natin siya sa area ng isang bakal. So you will have a total number of reinforcement of 1.24, which is equal to 2 pieces at top reinforcement. Sir, bakit po at top reinforcement? Kasi nga, since negative yung moment natin, yung tension sa taas, compression sa baba, yung tension natin nasa taas, kaya top reinforcement yung mangyayari. And after that, we will now check yung ductility niya. So, check for ductility for the next step. So, kunin ngayon natin yung value ng rho actual natin. Ko-compare natin siya sa rho max. Ko-compare natin siya sa rho minimum. So, kung yung rho actual natin that is greater than to the rho minimum but less than to the rho max, we can now say na ductile yung failure natin. So, kunin muna natin yung rho actual natin. So, yung number of bars natin dito sa rho actual natin is meron tayong 3 piraso ng 25 mm squared over yung width natin na 250 and effective depth of 400 mm. So you will have a value of 0.0147. And after that, kunin naman natin yung value ng rho minimum natin. So, in computing for the value of your raw minimum, meron lang naman tayong dalawang formula. And kung ano yung higher value between this formula for raw minimum, yun yung i-adapt nating value for raw minimum. So, gamitin muna natin yung unang formula natin sa computing for raw minimum. That is 1.4 over Fy. So, yung value natin for 1.4 over Fy, so we have 0.00337. And yung isang formula natin for raw minimum, that is equal to square root of F prime C over 4Fy. So, yung value natin dyan, that is 0.00356. So, i-compare natin yung dalawang raw minimum natin and the higher value, yun yung i-adapt natin. Upon computing, siyempre, yung nag-govern sa atin is eto, 0.00356. And then, after that is, papapansin natin na yung nag-satisfy naman yung condition natin. So, meaning to say, ductile yung failure natin. With that, we're going to check yung flexure natin. So with this one, check natin yung flexure para masabi natin na safe siya in flexure. So dapat yung MU capacity natin, that must be greater than or equal to the value ng MU max natin. So MU capacity, that is equal to rho. So, yung nominal resistance natin, multiplied by BD squared. So, we will have yung natin na 0.90 multiplied by yung rho natin. Yung gagamitin natin dito is the actual rho, 0.0147. Yung Fy natin na 415. Yung B natin, which is equal to 250 mm. Yung B natin, that is 400 squared over 1 minus yung rho natin na 0.0147 multiplied by 415 over 1.7 of F prime C na 35 megapascal. So you have a value of your MU capacity which is equal to 197.10 kilonewton meter. So which is greater than, so ito yung capacity nung biga natin to resist yung mga moments natin na pwedeng i-apply sa kanya. Wherein kung i-consider natin yung highest, natin dito, highest MU max natin, greater than yan to the MU max positive. So i-consider natin yung MU max positive kasi hamak na mas mataas naman yung positive moment natin dun sa negative moment. So kung mas mataas yung negative moment, yun yung pagko-compare natin. Kaso nga lang, yung highest moment natin dito is 155.648. Since mas mataas yung capacity ng beam natin, compared dun sa MU max natin, or dun sa maximum moment natin applied to our beam, so we can now say na safe in flexure yung beam natin. Sir, bakit po hindi na natin kinonsider yung weight ng beam natin? So kung babalikan natin yung problem natin, the beam carries a uniform dead load of 12 kilonewton per meter including its own weight. So nun sa initial computation natin, in-include na natin yung weight ng beam natin. That's why hindi na natin siya nire-compute ulit sa pagkuha ng maximum moment. Okay? So nakalagay na kaagad dun sa initial computation natin yung weight ng beam. Or na-consider na agad yung weight ng beam natin. So, meaning to say, safe tayo sa flexure. So, we will going to adopt 250 mm by 450 mm. Tapos, yung mga reinforcement natin, so meron tayong 3 25 mm diameter bars at bottom reinforcement. Kasi nga, due to the positive moment natin na 155.648, and you will have 2 pieces 25 mm diameter At at ano at top reinforcement. At top reinforcement found at the support. Bakit, sir? Due to the negative moment natin na 87.552. So, ganun lang yung pag-design natin. So, for this one, sa flexure lang tayo nag-design. Kaso nga lang, theoretically speaking, kailangan ka pa rin mag-design kung safe ba yan sa shear o kaya safe ba yan sa deflection.